All right, let's go ahead and get started. So this is going to be sort of a continuation of what we did from week one on structural analysis. We're going to lead into structural design. So one of the things that's kind of interesting, or at least I wanted to try and do for the first example problem that we will do is I wanted to try and take some of the concepts that we learned or talked about last week and at least try and apply them for the first example this week. And then as we go forward, we'll delve more deeply into the actual design stuff associated with steel and concrete. Now, before I actually start delving super in-depth into the examples, I'd like to take some time and look at this. So you all have been given the handout from the FE review manual, and I'd like to take some time and discuss what's in here, okay? It's worth mentioning because there's a lot of stuff that isn't in here and can definitely sort of gauge your studying. Now, for those of you who had me for concrete design, you'll know what I'm talking about. Before I go ahead. Well, that's a good point. Yeah, let me see if I can, if I have access to my V drive, I can. The internet was down in our offices today, so that's a good idea. Thank you, Mr. Canterbury. All right, so here's the FE reference manual. Okay, so let me make that bigger. Okay, so here on the left, got all the table of contents. Let's go to civil engineering. Okay, so I'm scrolling past the soil stuff, and now I'm into the structure stuff with concrete. So the first thing that you see is on the left, you see this big column of notation. Now, a lot of this stuff should be pretty familiar for those of you who had me for concrete design, the stuff like beta 1 for your rectangular stress block, the width of your member, the area of steel, area of shear reinforcement, all of that. You also see here on the top right, this is all your rebar sizes. So you've got your bar size, your diameter, your area. It's going to be fundamental for all the problems that we do. Let's see. Our fundamental relationships for stress and strain for 0.85 FC prime and for the computation of factored moments and whatnot. Our strain conditions, although more often than not, we're going to have a strain condition that's tension controlled. So remember, our phi value is most likely going to be 0.9. Very rarely do you have a phi value that's less than 0.9. So of course, that was that one question I threw on the test. Broke my heart. Broke my heart. You all remember that. You all remember that. Yeah, you got pretty close. You got pretty close. All right. We have a listing of phi factors or our resistance factors for our given components. Remember, we're essentially using load and resistance factor design. So we take our factored loads, you know, that whole 1.2 times the dead and 1.6 times the live to obtain a factored load. To obtain a factored resistance, we take our nominal resistance that we get from our stress block and our equations of equilibrium, and then we adjust that by a resistance factor. So you have different resistance factors for bending than you do for columns, for shear, and what have you. So everybody good so far? All right. Now, one of the things that's worth mentioning is there's actually not a whole lot of formulas in the manual when it comes to concrete. For instance, if you look at the section on beams, really all they list is singly reinforced beams for flexure, and that's it, you know. So the last edition of the manual that listed more formulas, I mean, it had a whole lot more. It had doubly reinforced beams. It had conditions for whether or not the steel yielded, for whether or not it didn't, or the compression steel, whether or not the compression steel yielded or not. There were T-beams listed, whether or not it was a true T-beam or a rectangular T-beam. Remember, that's where the depth of your stress block is. All that stuff was listed, and it's not listed anymore, which really means one of two things. Either during the exam they want you deriving this stuff, which is pretty unlikely if you're going to be doing a problem in 3 minutes, or the concrete stuff is pretty straightforward. It's not complicated. It's just singly reinforced beam. So our first design example tonight is going to be a singly reinforced beam. One other piece of advice that I would give you is that when it comes to beams, it's probably unlikely that you're going to be doing heavy design. If you remember from concrete design, if you're designing a beam, it's a highly iterative process. I mean, you're making guesses at the beginning, you know, guess, oh, the beam's about yay deep and it's about yay wide, and then from there you have a weight that gives you a dead load and you go from there. It's very, you know, it's very open-ended. There's a lot of right ways to do it. So because of that, it's probably unlikely that you're going to be like designing beams from scratch. It's mostly going to be analysis. Here's a beam, what is its FMN? So pretty much straightforward stuff like that. It also lists stuff with shear capacity, but again, I don't think you're going to do a full stirrup layout. There might be a situation where you need to determine given stirrup spacing in a given area, but that's about it. I mean, it's not going to be much more beyond that. There's a few points that are definitely worth mentioning. If you go to the first page and look at your terminology, you don't see any effective moment of inertia. So I don't really foresee very many deflection calcs. Remember that whole concept of development length? Don't really see anything with development length in here, do you? In fact, the only thing you see other than these formulas are your beam column charts. And it's really just one beam column chart at that. Remember, you calculate your Kn and your Rn parameter. Let me pull that up. So you calculate those dimensionless Kn and Rn parameters based on your column axial load and your column bending. Find the nearest chart, or the nearest point on the chart, and that gives you your reinforcement ratio. Take that reinforcement ratio, multiply it by the column area, and that gives you the amount of steel you need to put in the column. That's about it for beam columns. And honestly, that's about it for reinforced concrete design. You know, for those of you that took me last semester for concrete, we went way more in depth than that. We did development length for hooks, for straight bars. We did effective moment of inertia, looking at short-term deflections, long-term deflections. None of that stuff's on the FE at all. It's really just fundamental, straightforward stuff. Okay, so I want to explore that fundamental stuff with these few examples. So let me go back to the PowerPoint. So these are the topics that I really want to cover tonight. So for reinforced concrete design, I really just want to look at fundamental moment capacity, fundamental shear capacity, and fundamental axial capacity, and that's it. You know, that's really going to get you, by and large, all the way there. Then we're going to take a break, and we're going to look at steel design. Now, when it comes to steel design, we might as well take a look at it. There's a lot more going on in the manual when it comes to steel design. For instance, the equations that are provided are a lot more comprehensive. For instance, if we're looking at beams, we've got the whole kit and caboodle when it comes to the LTB curve. So we've got our plastic moment capacity. We've got our LTB curve for inelastic lateral torsional buckling. No elastic lateral torsional buckling, but if you remember, you really don't want to design beams in the elastic range anyways, so you always want to keep it inelastic. CB is given, so it's possible you may have to calculate your moment gradient modifier, and there's also some fundamental cases, which is more likely you're probably going to deal with your fundamental cases. Columns, you've got your Chapter E column strength equations. Remember, inelastic buckling and elastic buckling. If you notice a theme with my discussion, most of the stuff in steel design is really going to be beams and columns, and it's because of the information that's given. That'll make sense as we move through with this. Now, there's actually one part in the manual that's actually worth mentioning. I actually deem this to be an error in the manual, and for those of you who had me from steel design, you'll definitely know what I'm talking about. Well, I'll say this, maybe not an error. Well, I guess maybe not an error. I guess it's more just a bookkeeping thing. Oh, they fixed it. Okay, never mind. So this is something I want you to be aware of. So if you remember when we calculate a net area, you take the bolt diameter and add what?
You have 16, 4, and 8.
You add an, okay, you add a 16th when you're doing bolt calcs, but you add an 1/8 when you're doing tension member calcs. Y'all remember that? So this formula, it looks like it's wrong, but it's actually not, because it's saying the diameter of the hole, and the diameter of the hole is the diameter of the bolt plus the 16th of an inch. So it looks wrong. They didn't have, if I remember correctly, the last edition of the manual, they didn't have this listed, so it looked like it was wrong, but I guess they fixed that. So yay for the folks who wrote the manual. No, you don't need a full-blown steel manual. They summarize just about everything you need, and if you look at the summary, it's mostly focused towards beams and columns. I mean, you have this nice set of formulas for tension members, but for the most part, you're going to be doing beam and column stuff. The reason I say that is because if you look at the next page, okay, so next page you've got properties of wide flange sections, so you've got W21 or W shapes. Okay, so if I take a W21 by 44, what's the 21 mean?
21 inches in nominal depth.
It's about 21 inches deep. It's not exactly 21 inches deep. It's about 21 inches deep. Nominal depth. What's the 44 mean? 44 pounds per foot. So that's what the notation means for rolled sections for those of you that didn't have steel design. So 21 is about how deep it is, 44 pounds per foot. Okay? You're given the area, the depth, the web thickness, the flange width, the flange thickness, all of the flexural properties for IX and IY, or for the x-axis and y-axis, although you don't necessarily need them. Now, let's take a look at this table. Y'all remember this table? That's the ZX table. All right? Remember, you use this for beam design, right? Remember, just calculate your moment and find the, if you've got a continuously braced beam, find the first beam that works off the MP column. Now, if you notice, each of these columns are sort of grouped. And notice how the top line is bolded. Y'all remember what that bold line means in a group? It's the lightest section in that group. Like if I take this group here, the second group down, I've got a W10 by 88, W14 by 68, and so on and so forth. Of this group, the W21 by 55 is the lightest, and it just happens to be within that group the shape that'll get you the most efficiency. So if you're designing a beam and you calculate a factored moment of, I don't know, 450 foot kips, don't pick the W18 by 60, pick the W21 by 55 because it's lighter. That make sense? Pretty straightforward. Okay, in addition to plastic moment capacity, we're given the variety of stuff for our LTB curve. We're given the reduced yield moment for residual stresses. We're given the slope of that line. Remember the inelastic curve. We're given the anchor points, LP and LR, IX, and then our shear capacity. So we have moment capacity and shear capacity. But remember, in beam design for steel, shear doesn't matter. It's such a non-issue. Remember, just because of the way we manufacture rolled shapes, I mean, you get 20 kips of load and like 200 kips of resistance. It tends to not really matter. All right. All right. Now this is your beam chart. Y'all remember that from steel design. This is if you have a beam that is discretely braced. So remember, like, if your beam is continuously braced, it can fully reach MP. But if it's discretely braced, you go to this chart. Remember, this chart is based off a CB value of 1. So you'd scroll down here. So if you had your beam braced, I don't know, every 10 feet, so you go to 10 feet, and maybe your moment is, I don't know, 330 foot kips, so you find that point there. Go to the first solid line you see, and the first solid line you see is the W21 by 48. Why am I going to the solid lines as opposed to the dashed lines? It's the same reason I'm going to the bold lines in those tables as opposed to the non-bolded ones. It's the most economical shape. Remember that? All right. Okay. Remember this. These are your buckling effective length factors for columns. Never, ever, ever, never, ever use the theoretical values. Remember, you're always going to use the recommended ideal values. They threw them in there probably because this is the way the image looks like in the code. If you remember opening the steel manual, that's what the table looked like. They provided the theoretical and the recommended values so that if you ran some software program and were trying to evaluate its effectiveness in calculating buckling loads, it's probably going to spit out the theoretical values to you. But from a recommended design standpoint, use the ones below. So if you got a fixed column, don't use 0.5, use 0.65. And remember, these are your end-condition codes. So if I'm looking at column D, that is a column that's pinned on the top and pinned on the bottom. So the ends are free to rotate, so that's a K value of 1. Everybody good? All right. So down below that, our familiar alignment chart. Most likely you're going to be dealing with a moment frame. Remember, you do your sum of I over L for the columns over sum of I over L for the girders to get a rotational stiffness on the top of the column and on the bottom of the column. Draw a straight line to get K. It's probably unlikely that you're going to do a lot of that on the test. I mean, you may have a problem where you do 1 or 2, but you remember those problems, they take a while. It's not something that is quick. So it's something worth mentioning. All right. Now, this one is definitely one that I would bookmark or indicate in your head. If you all remember in steel design, there was a few different ways that you could calculate the capacity of a column. Now, you could just brute force it and use the equations, but one of them is that you could use the slenderness and based off the slenderness get a factored stress straight from this table. Take the factored stress, multiply it by the area, and there's your column capacity. The reason why I mention this, if you got a problem that says how strong is this column, don't use the equations, use this. It's a whole lot quicker, okay? I mean, it is a time test, so, you know, any edge that you can have on time, take it. So we might see if we can use this tonight depending on our examples, but we'll see. And finally, now this table probably doesn't look familiar right off the bat, but this is table 4.1. Remember the design table where based on a KL in the y-axis and based on a load, you can pick a family of W14s, W12s, and W10s. This is the table from which you actually select columns and then check them later. Remember, you select based on the weak axis, and then you have to go back and check strong axis by calculating KX LX over RX RY. But if you notice, they don't give you RX over RY. So what does that mean? Probably going to cover by weak axis. And if you're governed by strong axis, it's most likely an analysis problem as opposed to a design problem. And if you're wondering, any of these columns that stop short, it's because that's when KL over R exceeds 200, and that column isn't even economical anyways. So, in fact, spec even pretty much outright says don't use KL over R over 200. Because that's a really slender column, and we're talking stability issues there. Any questions? Okay. Now, again, we are going to do the first part of this session in concrete, and then we're going to go into steel. So let's go and look at example 1. So let's sort of take into account what's going on with this. I took this problem from a design guide I thought was pretty reasonable. Some of the numbers maybe I have a little bit of issue with, but ultimately I think this problem is a wonderful starting example for what it is we're going to do tonight. Now, for those of you that have calculators, I might require you all to do some number crunching for me, but we'll see what's going on. All right, so I got a beam that's 10 foot long, and it's got this cross-section shown. And if you look at the cross-section, the numbers are actually fairly small. It's being subjected to a uniformly distributed service dead load of 5 pounds per foot at concentrated service live load at midspan. They didn't give us the live load. So there's some point load at midspan. We don't know what it is yet. All right. Now we've got material values. We've got FC prime is 3,000 psi and FY. Oh, whoops. All right. I got to make a change. Sorry about that. This is 40,000 psi. Apologize about that. That's supposed to be 40,000 psi. All right. So FC prime is 3,000 psi. Fy is 40,000 psi. If I want to get nitty gritty with it, maybe I should make those subscripts. Maybe I should make that sub equals and control equals. Do that. Make that subscript. What's that? Control equals. Control Shift plus, like if you do Control equals, it's a subscript. Control Shift equals is a superscript. Works everywhere. No, actually, it might not work in Excel. It might not work in Excel. Because that's the font. You have to go in and modify it. Yeah. All right. So taking the FC prime to be 3,000 PSI and FY to be 40,000 PSI, I want to know what the maximum live load in the center can be according to LRFD load combos. And we've been given a series of choices. So with that, let me go into my little smart notebook here and see if we can start doing some figuring. All right, so let me minimize this. What is that? Okay, so okay, I'm going to take that and move it up here, and maybe that'll work. Okay, all right. So we're looking at this example. So we have a beam that's 10 foot long, and it's being subjected to a uniformly distributed dead load and a concentrated live load. Let's deal with the load part first. So here's the beam. I want to see something. So here's the beam. And that beam is 10 foot long, and it is being subjected to a uniformly distributed dead load of 5 pounds per foot. I know that seems kind of small, but the beam itself is rather small, so it's all evened out. And then we've also got, hold on, maybe I should also indicate that that is a distributed dead load. Then we also have a live load at midspan. I'll draw that blue. Yeah, that's a fair statement. Probably should have added that to the problem statement, but yeah, that's a fair assessment. And this dimension is 5 feet. Okay. So after what we did last week, this problem should be pretty straightforward, right? It's just a beam with a uniformly distributed load and a point load. So let's see if you all can tell me what is the moment due to the dead load. Does anybody remember the formula? Sorry. There we go. WL squared over 8. You all remember where I'm getting that, right? Well, you can do that, or you can just say, like, here's your shear diagram, right? There's your shear diagram, and that height is going to be the reaction, WL over 2. That distance is going to be L over 2. So the area is 1/2 WL over 2 times L over 2. So WL squared over 8. Fair statement? All right. Okay, so that's 5 pounds per foot times 10 feet squared over 8. So that is, let me get this screen lined up better for me. Okay, so 10 times 10 is 100 over 8 is 12.5 times 5 is 62.5 foot-pounds, right? Did I do that right? Yep. Okay, now, let's see if you all can tell me what is the expression for the live load moment going to be? PL over 4. So P sub L, L over 4. And you get that if I look at the shear diagram goes up, P over 2, and that distance is L over 2, so the area is P over 2 times L over 2, PL over 4. Y'all remember that? Okay. So that is PL times 10 feet over 4. Maybe I should write that in a little bit more of a subscript fashion. Clear it up a little bit. PL 10 feet over 4. So it's PL times 2.5 feet. We don't know what PL is yet, right? Everybody, is that fair? So therefore, I've got dead load moment, I've got live load moment. What can I do with that? Okay, so factored total moment is what? There we go. Yes, sir.
It doesn't state specifically in here, are there any assumptions that we just believe we don't have to take into account the weight of the beam?
That's another good point. And I'll say this. Unless stated otherwise, you probably want to at least consider it. But where it is concrete, we weren't provided with a self-weight. Like a unit weight of concrete. Like you can assume like 150, that's a common assumption, but it is that, an assumption. So, fair statement? All right. So 1.2 dead plus 1.6 live, that is 1.2 times 62.5 foot-pounds plus 1.6 PL times 2.5 feet. So MU is 1.2 times 62.5, like what is that? What's that? 75 foot-pounds plus PL times 4 feet, right? Okay, so this, if you want, we can call this like equation 1. Like we can call that equation 1 if you want. Is that a fair statement? Okay. Everybody good? All right. Now, okay, so that's the analysis part. Let's take a look at the strength of the beam, okay? Everybody good with that? So I'm going to take this. Oh, here, I'll do this. Is that good? All right. So let's take a look at the beam itself. So what's going on with the beam? We got a beam it's rectangular, and we got the top is 12 inches. We've got some bars going on here, and it said that they were 3 number 9s, right? And our effective depth, D, is 15 inches, right? Okay. Now we were also provided with FC prime is 3,000 PSI, and we were provided with FY is 40,000 PSI, right? So if I look at this from a strain perspective, we're looking at ultimate strengths, right? So if I were to look at my strain profile, it's going to look something about like this, right? So I'm going to say about like that, right? A linear strain profile. We defined this distance as, give myself a little bit of room to write. that as the neutral axis distance C from the center to the neutral axis. Let's see if y'all remember. What's that top strain up here? What's top? At the top of the beam, what's the strain? If we're talking at the ultimate moment capacity, what is the strain at the top? Does anybody remember that? It's a constant value. It's a number.
Is it steel?
Nope.
Is it
No.
steel modulus of steel?
Mm-mm. Ah. 0.003, right? Remember, you always assume that the strain at the top is 0.003, right? And then down here, like, y'all bear with me, let's see. So I'm looking at the 3 number 9s. So if I extended this out, would you agree that that value is right here, that is epsilon in the steel, right? And then this distance here, that is D minus C. Or no, that's D. Sorry, that's D. I'm getting my distances backwards. I'm jumping ahead of myself is what I'm doing. All right, so far so good? So you all remember from similar triangles, this distance right here, that distance is D minus C. So from similar triangles, I can say 0.003 is to C as epsilon sub S is to D minus C, right? Y'all remember that? And therefore, epsilon sub S is 0.003 D minus C over C, right? Now, let's see if y'all remember, what is that used for? Like, why do I care about the strain in the steel? What's that? Phi value. Remember, if the strain in the steel is above a certain value, that means the beam will behave in a ductile fashion, and therefore we can achieve a resistance factor of 0.9. Tension control. Remember that? All right. Now that's our strain profile. Let me move my little pen box thing over there. All right. Now, this is bringing it back, isn't it? Y'all remember this? Bringing it back. Now this is going to be my stress profile. All right. Now remember, we're dealing with concrete, and concrete is a material that's very, very strong in compression and very, very weak in tension. So in the tensile region, there is no resistance from concrete at all. So if I take this neutral axis, that's C, sort of extend it on, so that's my neutral axis line right there. If I take my C distance and extend it, I see no effect from the concrete below. The only force that I see on the bottom is this tensile force right there, which for singly reinforced beams, I can assume that that force has yielded, but then again, they have to yield because the strain in the steel has to be greater than 0.004, if you remember, so it has to yield. So if I want to calculate that tensile force, how do I calculate it? It's the area of the steel times what? Fy. Okay? Now that is the force that is in tension. For the force that's in compression, remember in real life what it would look like is this. Like here would be my my neutral axis or my neutral line. Here would be the neutral axis, and if you remember, concrete is a very nonlinear material, so in real life it would look like that, like it would be nonlinear, and we'd have to calculate the area of that. But we're engineers, we don't like to integrate stuff if we can avoid it. So we represent this shaded area right here with an effective rectangular distribution. or meant to do that in blue. So we represent that with an effective rectangular distribution. Remember that? So our stress block up here, it's a little bit above, acting in compression. Okay? And what is the width of that stress block? It's not FC prime, it's how much FC prime? 0.85. And that is always true. Remember, that's our empirical relationship that relates this nonlinear area. That's the relationship that'll give us an equivalent moment. Okay? Now, our stress block does not go all the way down to C. There's a little bit of a gap. And if you remember, what's the depth of that stress block? It's A, right? And how do we calculate A? It's beta 1 times C. Y'all remember that? Bringing it back, aren't I? Let me extend this. And, oh. No, that's supposed to be A. Here, I can rewrite it a little bit. So A equals beta 1 C. Fair statement? Fair statement? All right. So here's the thing. We have a model that represents what we've got going on in terms of our concrete beam, but we have to be able to determine what these forces are. And how do we determine what those forces are? We use equilibrium. In other words, all the forces in compression have to equal all the forces in tension, otherwise the beam's running away from us, right? Everything's got to balance out. So if I drag that down to where I can see it, if I recognize that compression has to equal tension, what is the magnitude of my compressive force? It's my compressive stress times the area, right? So what's the stress? It's 0.85 FC prime, right? Now that stress block is acting over a depth A, but it's acting across the entire width of the beam, right? So it's acting over that, what is it, 12 inches? Because the beam's 12 inches wide. So it's 0.85 FC prime AB, right? That's the compressive stress in the beam. It must be balanced out by the tensile force in the beam, which is the area of steel times Fy. That make sense? Now, we know that FC prime for this beam is 3,000 psi. We know the beam is 12 inches wide, and we know the area of steel. Well, let me ask you this. Let's talk about the area of steel. How many, what is going on with the steel? What do we have in this beam? What is it? 3 number 9. So, first page, we have our ASTM standard reinforcing bars. We are dealing with number 9 bars. So what's the area of a number 9? 1 square inch. Remember that? Number 9s. They always made my life easier when making problems because number 9s were 1 square inch. So 3 number 9s are 3 square inches. So looking at our problem, if I use my little pen thingamadoodle, blue, all right? We know FC prime. We know B, it's 12 inches. We know the area of steel. We know Fy. So what don't we know? A. We can solve this equation, and what it will give us is what is the depth of the stress block required to meet equilibrium. So therefore, A equals AS Fy over 0.85 FC prime B. Now remember, and I can't stress this enough, the 0.85 and the beta 1 technically are different values. They might come out to be the same number, but they might not. All right, so 0.85 FC prime times FC, whoa, I didn't even plug it in. My goodness. Oh. FC prime is 3,000 PSI. B is the width of the beam, that's 12 inches. All right. AS is 3 square inches. And 60,000 or no, 40,000, sorry, 40,000. All right, so what does that give you? All right. Okay. So we can do a couple of things with that knowledge. So if I go back up to my stress profile, so I'm looking here in this top right corner, I'm looking right here, okay? That A distance, what it did is it told us what the value of A needed to be such that C equals T. So this force and that force are identical, right? So how do you calculate a moment? It is a force times a distance, right? So if I want to calculate the moment capacity of this beam, I say the moment capacity is force times distance. So I'll say, therefore, moment capacity is force times distance. Now, what is the force? Well, which one has less symbols in it? 0.85 FC prime AB or ASFY? ASFY. So instead of multiplying 4 things, why don't I multiply 2 things? So my force is, we'll drag it down, ASFY. Now that takes care of my force. What about my distance? Well, my distance, if I go back, I'm looking here in the top right on my stress profile. Would you agree that the resultant of my compressive force is probably going to be somewhere right there? Not like that, right? Like if this is my stress block, and it's like a distributed load, then the middle of it's about halfway down, right? So can you all tell me, just looking at my stress block, how far is it from there to there, right? Because remember, it's a moment. I need force times distance. So let me erase that so I got enough room to write. D minus 1/2 A. There you go. Because from the force all the way to the top is D. The stress block is depth A, so half that down, there's your stress block. So the distance is D minus A over 2. So plug and chug, you get ASFY, that is 3.00 inches squared times 40,000 PSI times D. What's D for this beam? 15 inches. Remember, it's from the top of the beam to where the rebar is, minus A over 2. We just calculated A, 3.942 inches over 2. And that, I'll put that down here. And that equals, you tell me, what's it equal? Like that? That's inch pounds, right? So if I go back to my previous problem, all that stuff was in foot pounds. So how do I convert that to foot pounds? Divide by 12. So what do I do if I divide that by 12? What do I get? 130,400 foot-pounds. Now that's MN, right? Now you'd be tempted to take that MN equation and plug it in up top, but we're forgetting something, aren't we? We're phi MN. There you go. So we got to figure out phi. Now how do we figure out phi? Strain. There you go. So in order to calculate the strain, we need C, right? Now how do we calculate C? Well, A is beta 1 times C. So therefore, we need C is A over beta 1. Now A, that's simple. 3.942 inches. What's beta 1? Well, go to our handy-dandy little guide. So I know this equation looks like a mess, but here's a simple way of interpreting that equation. All right? Here's a simple way of interpreting that equation. I'm going to draw it over here on the left. Okay, so watch this. This little beta 1 equation. All right, so I'm going to say FC prime in PSI. And I'm going to say, what's beta 1? All right? All right. Now, if you're dealing with any FC prime value that's less than or equal to 4,000, this is 0.85. And then every 1,000, you drop an increment. So if this was 5,000, this becomes 0.8. You drop 1,000, this becomes 0.75. You drop 1,000, or add 1,000, I guess you'd say you drop 0.05. And if it's anything, actually, whoop, my symbols, that's supposed to be less than or equal. If this is greater than or equal to 8,000, it stops at 0.65. Y'all remember that? All right. So going back to our problem, what's beta 1 going to be? 0.85. Now, here's the thing. It just happens to be, I'm going to drag it up here. It just happened to be that this number way up here and this number way down here just happened to be equal. Pure coincidence. All right? They are independent numbers. Okay? Independent numbers. Talk about that 0.85 FC prime way up top and the beta 1 down below. It just happened to be they came out to be equal for this problem. They are independent numbers. All right? Plug and chug, and for C, what'd you get? 4.64 inches, right? All right? Now, what am I going to use C with? I'm going to use C with that right there, with my strain profile, because I need to calculate what the strain in the steel is. So I'm going to use it with this. So epsilon sub S is 0.003 D minus C over C. So D is what, 15 inches? Minus 4.640. 4.640. What do we get? 0.337. Okay, so this is a beam that's phenomenally ductile. Remember, we want that number to be above 0.005 because that indicates high ductility. This is above that, so it's highly ductile. So epsilon sub s is greater than 0.005. Therefore, phi is what? Phi 0.90. And therefore, phi mn is 0.90 times 130,400 foot-pounds, right? That was the moment capacity we calculated. And what is that? So that's my equation 2, if you will. Oh, I know. Everybody good so far? So here's what we calculated here, phi mn, that is the capacity. That is how much the beam can hold up, right? Now, if I scroll up real quick, if I just scroll up way up here, that equation 1, that was what the beam was being subjected to, right? So phi mn has to be greater than this 75 foot-pounds plus PL over 4, so I can set those equal to one another and solve for PL. 75 plus PL times 4. So, and I can scroll up and down as much as you all would like. So I'll say set 1 and 2 equal. So 117,360 foot-pounds equals 75 foot-pounds plus PL times 4 feet. Can you all solve that equation on your own? What does it come out to be? So what is the answer to the problem? Most nearly 29,000. So B, I should probably put most nearly. All right. Oh, here, let me move this out of the way. Equation 1 was when we did that. Remember that? Like the analysis. So like, oh goodness, let me get that out of the way too. Okay, so PL over, the equation 1 was when we did the analysis of the beam to get an expression for how much moment was on it. And then all that crap we did just now was how strong it is. Now, this might, sorry, voice is going, done a lot of lecturing today. It might have seemed a little excessive because if you look in the manual, all those formulas that we just derived, they're in the manual. But the point was to review the material. So I figured let's just redo it again. But if you look on page 3 of this little handout that I gave you, here I'll even pull it up on the screen real quick so you all can see it. Let me, come on. Old keyboard beside it. There we go. Let me go back to my PDF. Go up a little bit. If it decided to load. Okay. Okay. Let's try that again. Okay, so here's page 1 of the handout I gave you. Here's page 2. I said page 3. It was page 2. But if you look at all these formulas, so, going through this, how do we calculate the strain in the steel? 0.003 D minus C over C. How do we calculate phi? Well, phi is 0.9 when that strain is greater than 0.005. How do we calculate the depth of our stress block A? It's ASFY over 0.85 FC prime D. How do we calculate nominal moment? Well, we can do the compression force times D minus A over 2 or the tensile force times D minus A over 2. In the end, it's the same. How we? Yes, sir.
Is the problem that you just gave us, is it going to be just a calc crunching problem, or is there another way that we can maybe get that a little quicker?
Oh, there's a. I mean, to be honest, the way. I mean, you can just follow this. I mean, I was drawing the stress profile and the strain profile, and oh yeah, remember the top strain's 0.003 and all that. I mean, we were doing a lot of review with that problem. I sort of used it as an excuse to go through a lot of that. You don't need to do that. And the next 2 problems, it's really going to be just plug and chug. So.
Well, even without that, I mean, there's still quite a bit of calculation. I mean, is there any way just to look at it,
Well,
think to yourself?
No, well.
Can we make some assumptions?
Well, there's a couple observations you can make. So number 1, the dead load was like 5 pounds per foot. It's nothing, This table weighs 5 pounds per foot, more than that, and we're talking about, concrete beams, So you could almost just, the dead load of that 5 pounds per foot, just disregard it. It's nothing, and just handle it by itself. That's a little bit of calculations you can do. Let's see, that's one way of shoring it up. Another way of shoring it up is it's highly likely that phi is 0.9, highly likely. So, I'm not saying ignore it, but you could probably just assume phi is 0.9 instead of having to do the strain check and then that. You assume it at your peril, but it is not the craziest assumption in the world. So.
If you're running out of time and have one of these problems, then just
go ahead, yeah, go ahead. So really what you could do is calculate your moment as PL over 4, bam, bam, 0.9, solve, No, not with this problem. They're too close. They're too close. It wasn't like that last where one of the answers was 0. So. Want to go for another one? The other 2 for concrete are going to go much quicker. Much quicker. Okay, so let me review this problem really quickly. This is a pretty straightforward problem. There's really one big point I want to make about it. So this problem, you have a singly reinforced concrete beam. You have FC prime is 4,000 psi, Fy is 6,000 or 60,000 psi. Looking at the beam diagram, we have a width of 18 inches and effective depth of 33 inches. We got 7 number 6 bars on the bottom, and then the big thing is our stirrups. Remember, our stirrups are meant to resist what type of force in a beam? The shear, okay? This one, we have number 3 stirrups spaced at 12 inches. We have a 1.5 inch cover, although that shouldn't really matter too much to us. And our question is, what is the shear capacity? What's the shear capacity? So, pretty straightforward problem, isn't it? Let's see. Let's see what we got. Now, all right, you all have your manual right there, so full screen. All right, so, okay. Now, so first off, can somebody tell me what phi is going to be for this problem?
0.65.
Nope, not 0.65. Check your first page. Say it again. No. What are we looking for? 0.75. There we go. Big money, no whammy, no whammy, no whammy, no whammy, no whammy. Stop. Now, we're dealing with a shear problem, so phi is 0.75. Moment is the only situation where you actually have to determine phi. The others, it's a lookup. Okay? So phi is 0.75. All right? Now, we're trying to calculate phi Vn, right? So phi Vn is our goal. So how do we calculate Vn? All right, this is really going to be plug and chug. All right, what does the manual say on the second page, page 154? How do we calculate Vn? Vc plus Vs. Now, how do we calculate Vc? Here, I'll go ahead and put the W. Fc prime. Okay, now, all right, remember anytime you see that square root of Fc prime, it is an empirical relationship, which means you put in PSI and you get out PSI, okay? So if I plug and chug, this is 2 times the beam width, which is, what, 18 inches, times the effective depth, which is 33 inches, the square root of 4,000 PSI equals, if you plug and chug, that'll give you, what is that, 75, 135.7, something like that? All right. Vs, how do we calculate Vs? AV Okay, now, all right, so let's check this out. We've got number 3 stirrups, right? So what's the area of a number 3? 0.11. So what's AV? 0.22, all right? Because we are looking at, here's our beam. We are assuming that a crack crosses those stirrups. Therefore, we don't cross one number 3, we cross 2. So our area, where's the full screen? There we go. There. Our area of shear reinforcement is 2 times 0.11 inches squared times, what is it, 60,000 psi? The beam depth is what? 33 inches. And S is 12 inches because the stirrups are spaced at 12 inches. Remember, the closer your stirrups are spaced together, the stronger the beam is because it's more steel. All right? Plug and chug, and that gives you about 36,300. So therefore, Vn is Vc plus Vs, which is 111,436, and phi Vn is 83,577 pounds. So what's the deal? Remember, the two big things about this problem. A sub V is the area of the stirrup, and because we have a U-shaped stirrup, it's not the area of one number 3, it's the area of 2 number 3s. The other big one is square root of Fc prime. You put in PSI, you get out PSI. And that's all there is to it. Remember, it's an empirical relationship that shows up a lot in these equations. Remember, a lot of these equations we use in concrete design, they're not, I don't want to say mathematically rigorous because they definitely fit the test data and even some of the theory, but they're not friendly when it comes to units. They are empirical. See, this one's simple, isn't it? Next one's going to be even simpler. You all good? I could wait if you. I mean, we'll take a break after the concrete section and then move on to the steel section. It's all right. We'll take like a 5-minute break. After this, I'll probably at least need a glass of water. But I can leave that up for a second if you all want to write that down. What's that? Because, all right, I'll do my best with 3D art. So if I have a beam and it looks like this, then I've got some steel inside that beam, and then, I don't know, that's going like that. Then I've got, you know, some support like this. And then on top of that beam, I've got, you know, some load, whatever, right? I am assuming, remember, that those cracks occur at around a 45-degree angle, right? So it's going to crack, you know, about something like that. So my stirrup inside the beam looks something. Let me make it red. My stirrup looks something, I don't know, like this. Right, that's a stirrup. So that crack crosses the stirrup in two places, like right there and right there. So that's why we multiply by 2. Now remember, why do you assume that your crack occurs at 45 degrees? Mohr's circle. A state of stress under pure shear will experience principal stresses at an orientation of 45 degrees. Remember, it's compression one way, tension the other way. Concrete strong in compression, weak in tension, so it opens up with the tensile region, hence 45 degrees. I swear that theoretical, that Mohr's circle stuff, it happens. It actually has benefit. I can't believe it. I'm pretty proud of my 3D art skills on that. I think I did pretty good. My 3D art skills. All right, everybody good on this problem? Again, it really is just plug and chug. And the next one is going to be even simpler. If I look at the next problem, okay, all right, so the next problem, okay, so we did a moment assessment, we did a shear assessment, now we're going to do an axial load assessment. So now we've got a column, okay? So now we have an element and we're just pushing on it. And here's the cross-section. It's 16 by 16, 4,000, 6,000 PSI. We have 8 number 9 bars. What's the ultimate strength? What's VPN? And tie reinforcements are utilized. So we're not using spirals. Remember, spirals give better confinement when the outer part cracks. So you actually get a little bit of a higher phi value because of it. But all in all, straightforward. Everybody good? All right. New page. Full screen. Ooh, my pen dropped. Okay. All right, I guess that kept it there. All right. So we've got FC prime is 4,000 PSI, FY is 60,000 PSI. All right. We're looking at short columns. So if I look right here, design strength of tied columns. I'm on the second page. It really is plug and chug. So Phi value is what? Phi is 0.65. All right. So phi Pn is 0.8 phi times the following. Oh, I don't need that. .85 FC prime times gross area minus the area of the steel plus area of the steel Fy. Now, what is going on with that equation? All it is it's saying that we take 0.85 FC prime times the concrete, which is the whole area minus the area of the bars, and then area of the steel times Fy. Phi's incorporated, and we have our 0.8 to account for that unintended eccentricity. So we've got 0.8, 0.65 times 0.85. FC prime is 4,000 PSI. I'm just going to go ahead and write 4 KSI. All right, AG is here, what is it going to be? 16 inches squared minus, now we have 8 number 9, so that's 8 square inches plus 8 square inches, 60 KSI. VPN is what? That one's a simple one, isn't it? Really, it was the beam stuff that I really wanted to review because I wanted to get y'all's minds thinking about concrete. And I think of all the stuff that you learn in concrete design, it's the stuff that's the most familiar. Yes, sir.
Could you give a quick rundown on how to deal with like a beam column situation since they get some sharp in there?
Okay.
Just real quick.
All right. Does everybody have this? I'm going to leave this up for a second, and then I'll go back to your question. Everybody good? All right. So here's what's going on with the beam column problem, and I might throw this in next year's review. Okay, so here I can probably get rid of that. There we go. Okay. So you can go away too. Here's your beam column interaction chart. So if you remember, these are basically just PM curves for different beam columns of different dimensions. So you can't do a beam column problem on the exam if they don't meet these specific dimensions. It has to be a column that's 4 KSI concrete, 60 KSI steel. You have to have a ratio of the total exterior width of the column and the distance between rebar of 0.8, or this won't work. So if you remember, this is an L 4-60.8 chart. Y'all remember that? Remember the legend? All right. So now you have an X and Y axis. So typically what would happen is you would be given a problem and you would have a load demand and a moment demand. So a factored moment and a factored axial load. So a factored PU, factored MU. Based on a phi value of 0.65 You then calculate a required Pn and a required Mn. The ratio of those two is your eccentricity, E, right? Okay? Based on those eccentricities and what have you, you've got FC prime. You can calculate the gross area. You know the height. You can calculate these two parameters on the x and y axis. Let me zoom out a little bit. You can calculate the Kn and the Rn. Kn being a value related to axial load, Rn being a value to moment. And then all it is this, okay? Go to the x-axis on Rn, y-axis on Kn, and find the appropriate point. Notice how those rho values occur in rings. You see that? Like there's a rho value of 0.01, rho value of 0.02, rho value of 0.03, rho, etc. Those rhos are reinforcement ratios. So this would be a reinforcement ratio of 0.01. This would be a reinforcement ratio of 0.02. Take that reinforcement ratio, multiply it by the area of the column, that gives you the area of the steel. Pick how much steel you need. And all there is to it.
So they're only going to give us something that when we use this, they're really only going to give us something if we have to calculate the area of steel that we need.
That's most likely, yes. Yes, that's most likely. Simply because, I mean, there's not a whole lot you can do with that chart other than that very aspect. I mean, they might turn it around and say, like, based on this value, compute E or something weird like that, but it's kind of strange, kind of out there that they would ask you to do that. So. Yes, that's why the chart is limited. In fact, they have to sort of be between that. Yes, yes. Yeah, yeah. You have too much steel, and you can have crushing and stuff like that. Not enough, and then you don't have enough ductility. So. Right. Is everybody good with this? Would you mind if we take a short recess and then hit steel back up afterwards? All right. Let's take a break. All right. So let's continue the review and discuss the steel design portion of the exam. Like I had said last time, or a little bit ago, if you go through the manual and review the design guide, you're going to find it very heavily focused in column and beam design. So I've got a couple problems that kind of explore that. So here's the problem. So from the choices available below, what's the lightest wide flange shape that can resist a service dead load of 125 kips and a service live load of 200 kips? So they gave us dead and live, and we need to determine what column is going to work. So for this column, we're going to take Kx equals Ky equals 1 and L equals 15 feet. So if Kx equals Ky, that means which axis governs, weak axis or strong axis? Weak axis governs. And if the weak axis governs, that means I don't even have to check the strong axis. It's really just factor the load, find the one that works. So let's go through this step by step. All right, so let me pull my little notebook here and get a new page, full screen it. All right, and I think I can actually write on the PDF in the manual, so I'm going to use that guide. Hopefully that works. So, all right. So what we got? We've got a dead load of 125 kips and a live load of 200 kips. So therefore, we can calculate a factored PU doing what? 1.2 and I have a feeling you all can plug those numbers in. 1.25 times 125, 1.6 times 200 comes out to be 470. So far, so good? So we know that Kx equals Ky equals 1.0, right? And we know that the length of the column is 15 feet. So that tells us a couple things. It tells us that because the K values are equal, that we automatically know that the weak axis governs. And that our KL in the y direction equals 15 feet. All right. Everybody good? Well, if they weren't equal, remember, if they aren't equal, then you design based off the weak axis. You select a series of trial shapes, and then for those trial shapes, you check the Rx over Ry ratio, which is, yeah, those are Kx and Ky. All right. You select a series of, a family of shapes, and then check based off the Rx over Ry ratio. But we don't have Rx over Ry ratios in the manual, so it's fairly unlikely that we're going to have to do that. All right. Everybody good? Now, I think I can write in the PDF using the super nifty technology here, so let's see if I can do this. So here's the PDF. Now, what I'm going to do is I'm going to go to this page, that one right there. All right? Let's make that big. Okay. So this is the available strength and axial compression table. So in other words, this is the table that we are going to use to select a column. Now we ought to be a little smart about this when we do this problem. I mean, let's look at the problem. Should I go out of my way to select any W14s for this problem? Why not? There's no W14s in the choices, so don't even worry about the W14s or the W10s for that matter, right? No point. In fact, all we need to do is worry about the W12s, okay? So watch what I'm going to do. Let me get my little pen situated, all right? What is KL? It's 15 feet, right? So I'm only going to look at those numbers. Y'all see that? All right. So I'm looking at those numbers along that horizontal line. Okay? Now what is our, let's just do this. Let's just do this. Let's make this simple. All right? We've got 4 choices to this problem. A W12 by 53, 50, 45, and 50. So that's going to be this, that, that, and that one, right? Y'all see what I did? So I'm basically just finding the intersections there. So what this is telling me is, like, if I look at the W12 by 40, if the column is 15 feet long, that's telling me it can hold up 280 kips. Is that column any good? No, because our load is 470, right? This one's no good. Can't use that one. What about 45? Can we use that? There you go. About 50. And what about the 53? So, what's the answer to the problem? Not too shabby, is it? Now, all right. You all have that? I'm going to erase it off the PDF if it's all right. Boop. Okay. Now, where's my little, oh, there it goes. All right. So now, that's pretty much all I've got to say for columns, at least for the purposes of this review. I mean, I could give you all like 8 more column problems if you'd like, but at some point we have to move on to another topic, and we know we've been here for a while. So let's look at beams. Okay, so we have a W24 by 55. It is to be used as a simply supported beam to support a uniformly distributed load, what is most nearly the maximum flexural capacity of the beam, if we take CB to be 1, which makes our lives a whole lot easier to deal with in the wonderful world of steel design. All right, now let me see something. I'm just curious. 24 by 55. Okay, all right, I was just curious. Okay. Now, everybody good? There are actually 2 ways to do this problem. 2 ways to do this problem. Okay? Now, we have been told that CB is 1. Okay? We've been told that CB is 1. All right? So, if you all recall, CB is the moment gradient modifier. In other words, when we draw moment diagrams, they're not very constant, are they? They're always up and down and up and down. But when we did our derivation for lateral torsional buckling, the column or the beam strength equations, we derived them assuming moment is constant. So we have to take that into account some way. So we take that into account with CB, with this term CB. So if we take CB to be 1, we're saying, ah, to heck with it, let's just assume the moment is constant. It's actually not an appropriate design philosophy if we were really designing, but this is the FE exam, and that's pretty likely. Now, one thing that might be worth mentioning is there's 2 ways of doing this problem. We're actually going to do them both ways. It's been a while since I had designed this problem. I couldn't remember if this was on the chart. All right. If you go to this page, this is our beam chart table in the guide. Now, if you remember, your beam strength equation looks a little something about like this. Let's see if I can draw it over here. So, if you have this is LB as the unbraced length, and this is your nominal moment capacity, your beam strength equation looks something like that. You have a flat region where that's MP. You have a linear inelastic lateral torsional buckling region, and you have an elastic lateral torsional buckling region as follows. Now, if you look at this beam chart, I know it looks like a damn mess, but really all it is are those LTB curves plotted for a whole bunch of shapes, all on top of one another. And remember, the solid lines are the lines that are economical. But if you want, you can actually look at the chart and see if you can get the answer. What's the shape that we're looking at? Isn't that a W24 by 55 right there? So there is a W24 by 55 on the chart. This is an unbraced beam. So what is the unbraced length? 12 feet. So watch this. All right, let's see if I can do this. I'm going to erase my little beam curve so I can see what's going on. All right, now let's go to this. You said 12 feet, right? Oh, let's see if I can do it. That 12 feet? Ooh, I crossed my 24 by 55, didn't I? Sure did. All right, so it's about like that. And W24 by 55 is, I think it's the top one. I kind of drew over it. So what's that value? About 344, 342, something like that. So what's the answer? B. That was simple, wasn't it? But I'm going to show you the math in case. Or maybe I needed to draw my line a little higher or something like that. But that's a simple way of doing it, right? Y'all see what I did? Now, let's go through and do the math, okay? Oh. Now, before we do that, Get my little eraser thingy. Now, if you all recall, let's go to the page before that. Here's our W-shaped selection table. This is our ZX table, right? Okay? Now, I'm curious if this will actually work. This is my first time, or second time, I guess, messing with this pen technology. Oh, I bet you this does work. Hey, look at that. Y'all see that? So I'm highlighting the row associated with the W24 by 55. That's the shape we're looking at. So let's see if I can draw my LTB curve out here. I know it's going to be small. So it's like that, and like that, right? Remember those terms down below? Those were LP and LR. And then this term is, here, let me see if it'll show up in black if I make it really thick. That is MR, and that's MP. Like that one's MP, and that one's MR. Y'all remember that? And then the slope of that line right there is BF, beam factor. Been a while, right? That's basically what we got going on. So if you notice, I've got, let's see, MP right there. I've got MR right there. I got BF. I've got LP. And I've got LR, right? So what is LB? What's the unbraced length for this beam, right? What is it? It's what, 12 feet we said? So would you agree that we are in between LP and LR? So that puts us in that straight line inelastic lateral torsional buckling region, right? Right? So I got to use my eraser, sorry. So I'm having fun messing with this, I'm not going to lie. So here's my equation then that I'm going to use. There's my equation right there. Now, I'm curious, I can't remember, I'm almost positive that the manual spits out the shortcut equation to you. It does in some fashion, all right? Does everybody have this equation right here? Or everybody seeing this? Okay. Now, if you remember how the equation says Mn equals this term such that it is less than or equal to MP? Remember what that means is that no matter what your modifier does, no matter what CB does, it could be 2, it could be 986, whatever it does, you cannot go above MP. It's impossible, okay? So no matter what, you are limited to MP. But for our problem, CB is 1, right? So because CB is 1, really our expression is this stuff in the parentheses, right? Fair statement? All right. So I'm going to do a little bit of computer magic here. Give me a second. All right. All right. So there's my equation, right? Right there. Now, let me sort of rewrite the stuff that matters. We don't have to deal with the stuff on the inside, or the less than, and we know that CB is 1. So it's MP minus MP minus, and then this 0.7 FYSX, that's just MR, right? LB minus LP, LR minus LP, right? Now I can rewrite this term over here on the right to say MP minus MR. I can put that. Oh, nope, I got that backwards. It's late, that's what it is. I can get that. No, I'm doing it again. I can do that, right? That's just taking that denominator and moving it over to the other side. This stuff right here is called the beam factor. That's just the slope of that line, right? Change in y over change in x. That's all that is. So I can say that my relationship is MP minus BF LB minus LP. So therefore, phi MN is phi MP minus phi BF LB minus LP. That's all there is to it. So phi MP for our problem, it's a 24 by 55, so what's phi MP? Going to the table, right? 503, first row on the table, foot kips, minus 22.2 kips. Y'all see that? First line on page 159. And then 12 feet minus 4.73 feet. So therefore, phi MN equals what? And what did we get when we looked at the graph? About 343, 344. That was just eyeballing it. 3, 2, 1. Everybody see where I got those values from the phi MN expression and how I did this derivation? They don't include the equation in the spec, but remember that the linear line is just the MP minus the beam factor times that difference. Everybody good? Now, it's totally up to you. We can go ahead and do the last problem if you like. It will take a little while. The only thing about the last problem is it is a tension member, and the only way to do a tension member problem on the exam is if they give you a lot of data. Like, I'll show you something with my tension member problem. Does everybody have this? Okay, all right. All right, so here's my tension member problem. In order to do the tension member problem, it's an angle. You had to be given a lot of data, and I mean a lot of data. You had to know it was an angle 6 by 4 by 3/8. You had to know Fy, you have to know Fu. You have to know that there are 5 bolts that are 3/4 inches in diameter. I'm sorry it's not showing up very well on the screen if my little pen thing works. There's one there, one there, one there, one there, and one there. So what, y'all steel design folks, what pops out to you? Stagger factors, because the bolt pattern is staggered. Your failure path is going to look something about like that. Because if I take this angle and I pull on it with some force P, it's not going to just, samurai sword straight through. It's going to fail along the bolt lines. You remember that? So In order to do that, you need all the dimensions, you need the gauge factors. Then this is an angle. Angle properties aren't in the manual, so you need AG and you need X bar. It's actually sort of a point I wanted to make in general about this example is that tension members are actually pretty unlikely on the exam because there's a lot of data that goes into it. I'm not saying you won't do one. I'm saying it's really more likely that you're going to do beam and column problems because of all the guides that have been provided to you. I can do it if you'd like, but it's a lot of work. How about this? I'll just email you the solution. How's that?
Sounds like a plan.
Does that sound like a plan?
Will you just make can you do this?
I can probably screencast this one. I'll just do it on my own. Take me 10 minutes or so. Because I have the Camtasia software on my desktop, and I have a Wacom Bamboo tablet, and I can just open up Smooth Draw and do it like that. It'll look a little different, but won't matter. You all good with this? Now, I know this went super quick, but you all have any questions about just the stuff on the exam? I mean, we actually did a lot of material tonight. In my opinion, we did a lot more than we did last week. Y'all good? All right, well, thank you. Let me hit the little stop button. There it is. And stop.